the opportunity to be here, and I'm very happy that this center is starting, and congratulations to Daniel and everybody else. So today I just want to give you an introduction on gravitational waves, mainly what's been happening observationally in the last decade or so, and so that's the focus of the talk. I will talk about gravitational waves as measured by LIGO, some ground-based experiments. I will also tell you about gravitational waves as measured by pulsar timing arrays, which is the latest detection of a background of gravitational waves. And then I'll also tell you a little bit about gravitational waves from the early universe, which you already heard about yesterday. So maybe if I'm running out of time, turn on my stopwatch I will go faster there. So gravitational waves, we're all in the same page, small perturbations of space-time. These small perturbations h mu nu, if you have a wave traveling in the, along the z-axis, they travel at the speed of light, they have two polarizations. The metric looks like that. The important part for astrophysics and cosmology is that these waves, first they travel in empty space, so we can see them from very far away. But furthermore, they interact extremely weakly with matter or not at all. And so the universe, for the most part, is transparent to them. So if they were produced at the early universe, they would still be around. If they are produced in very dense and strange astrophysical environments, they can come out, and so we can study phenomena that we were not able to study, including the beginnings of the universe, with light, say. So how do you produce gravitational waves? So if you have matter moving around, it produces gravitational waves accelerating. So in astrophysical context, the typical example is a binary system, two objects, say two stars, two black holes, a black hole and a neutron star, orbiting around. So they lose energy by emitting this gravitational radiation. As they emit this gravitational radiation and they lose energy, their orbit shrinks. So the period of the orbit then becomes shorter and shorter, and eventually they collide and they merge. So now to have some simple estimate, so you can ask the question, how does this merger time of a binary of two stars, how does it depend, or how does it compare, the time it'll take to merge, how does it compare with the orbital period of the binary, okay? And the formula is very simple, so it's basically given by the orbital period times c divided by the speed of the binary in which the stars move to the 5th power. So this means that unless the binary is moving, the velocities are comparable or not so small compared to the speed of light, the c over v to the 5th is a humongous number, and so it will take forever to merge. So for example, if you take the sun and the earth is moving at 30 kilometers per second, so this number is huge. So it'll take a very long time. So typically the emission of gravitational waves is very weak, and so it affects systems very little, except when we're talking about systems whose orbit is so fast that it's not so, so the period is short, and also the speed is not so different from the speed of light, and so at the end of the day, this merger time is not so long, compared, say, to the age of the universe, or compared to, in the case of LIGO, we want to see the two things merge, or we see the two things merge. So it's, we see tens of millisecond thing happening. So very fast they merge, and so this means that they are moving very rapidly compared to the speed, or close to the speed of light. So strong gravitational waves require compact objects orbiting very, very fast, because if if you think about the sun and you say, okay, let me just start bringing the planets closer and closer in so that the orbit is faster and faster with respect, closer and closer to the speed of light, and so you can emit something before it goes any fast compared to the speed of light, you're entering the sun, right? And so the whole thing is over. So if you want to be able to bring the things together more, there needs to, the thing has to be very compact so that the escape speed, which is also comparable to the orbital speed when they're very nearby, is close to the speed of light. Great. So, you know, we can go back to the beginning of this field. So an example of two pulsars orbiting around quite close to each other at a orbit of you know, almost 8 hours, and it was realized that they would you know, the emission of gravitational radiations will change the period of this orbit enough that if one track this and the pulsars are good clocks, and so one can track the orbit in detail. So this Hals-Taylor pulsar was tracked for some time, and the change in the orbital period that is produced by the emission of gravitational waves was compared with the actual observations of the orbit, the orbits, and you know, the prediction of general relativity was very you know, perfectly on top of the measurements, and this led to a Nobel Prize. And so this was the first indication of gravitational waves. At least, you know, indirectly, maybe that we didn't detect the gravitational waves, but we did detect their effects on the system. So this is just some simple estimates of if you have a mass m, say the total mass of the binary, and the frequency of the orbit is f. Then what are the formulas for the V over C, or the strain of the gravitational waves, which of course depends, that one would observe. Of course, this depends on the distance d, and here are some selected, at the bottom in the table, you can see some selected examples of numbers for something that are potential source. So for example, these are the numbers for the Hals-Taylor pulsar that I talked about. This is the first detection of gravitational waves from LIGO. So these were two black holes around 30 solar masses, much, you know, 400 megaparsecs away. This is a white dwarf in our a white dwarf binary in somewhere in the Milky Way, which would become a source for LISA. And this is two supermassive black holes of 10 to the 9 solar masses orbiting around very far away in the centers of some faraway galaxy. You know, these are the typical numbers, and you can see the size of the strain, the H, is very, very small in all of these cases, right? So measuring these gravitational waves is not an easy task, because it would produce changes in the space-time that are 10 to the minus 23 compared to the ones in the eta mu nu of the flat space metric, right? So these are very, very small. So of course, this is the good part about this is that then the universe, this is the reason the universe is transparent, because basically this is doing nothing, right? And so then we could look at the early universe by looking, or the gravitational waves, if they were produced there, we would still be around. Okay, as I said, there can also be gravitational waves not just from astrophysical sources, but there could be some cosmological background. What we discussed yesterday were cosmological background from inflation, maybe from the very early universe, something, you know, strange happened, produce also gravitational waves, they would still be around. But there might be other exotic phenomena happening at other times in the history of the universe that would, if the gravitational waves were produced, if there were matter moving fast or things of this nature, you would produce gravitational waves in enough quantity that we could detect. They would, in any case, always be around because the universe is transparent. But if they're strong enough, we may be able to detect. So. And the frequency of those gravitational waves left over would depend on when they were being produced. So we could try to, if we ever detected a background of gravitational waves from some early universe, in, you know, before Big Bang nucleosynthesis or what have you, by looking at their frequency, would we understand when this exotic process happen, and looking at this frequency dependent, we might guess something about what was it that was happening. So how do we go about detecting gravitational waves? When a gravitational wave is traveling, it changes space-time, and so if we have photons, for example, or traveling in this background of the gravitational wave, let's say we have some faraway pulsar that is emitting pulses and they're getting to Earth, and between, in the universe there are gravitational waves moving around. The frequency at which these pulses are getting to us will be modulated by the presence of the gravitational wave and the oscillation of these gravitational waves. So these pulses will arrive to us with some little delay or some, let's say it's a perfect clock that emits pulses, pip, 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 then we will not see it like that if the gravitational waves are in the middle. And so that's the basic effect that all of these detectors are using. The kind of detectors that people have used and have been successful at finding gravitational waves. I mean, of course, the LIGO is completely sure that they have seen gravitational waves. The pulsar timing array is the latest detection, which I suppose is a field that is just starting. So there is perhaps some possibility that the detection will eventually will not be real, but at the moment we all think that it is. So in the case of LIGO, what's happening is that in the presence of gravitational wave, the pulses or the clock, which in this case are the waves of a laser, they get the arrival time of this laser is being delayed or advanced compared, and the trick to make sure that you can detect this is to compare time delays along two perpendicular directions, and so the same laser acts as a clock. You're comparing one side to the other, so irregularities or problems in the laser cancel out, and that's why you can do it. You can see such a small effect because the light travel time in the arms of LIGO is microseconds, and the effect of this gravitational wave is of the order of 10 to the minus 20 microseconds. So it's a very small delay in these waves, but so you have to be very careful that the noise of the laser, for example, cancels out in your setup. Or equivalently, you can interpret this as a change in the length of these arms, which is very, very small, much smaller than the size of a proton. So it's kind of fun to go through and trying to understand how is it even possible that such a measurement has been done, but I don't have time to go for it. But in the case of pulsar timing arrays, what's happening is that there are these neutron stars around the galaxy that are rotating very fast, and they act as clocks. They have these pulses that move around and go along every so often. In this case, they are millisecond pulsars, so every few milliseconds you see a pulse from this beam of light just crossing the line of sight towards the Earth. So they act as clocks, and if there are gravitational waves passing around between the pulsars and the Earth, they delay or advance the arrivals of these clocks, of these pulses, and by comparing in a way that has a very predictable pattern on the sky of how, depending on the orientation of the gravitational wave and so on, if this one is delayed, the nearby ones also has to be delayed, and the other one, the pulses from some on the opposite direction has to change in a very particular way, and so that's what was detected. And in this case, for the gravitational waves that they are detecting, the time delays produced by the gravitational waves are nanoseconds, tens of nanos. Okay, so these are the ways that people have detected gravitational waves. Of course, there are gravitational waves of every frequency. These ground-based observatories are tuned to detect gravitational waves of around 100 hertz. The pulsar timing arrays are in the tens of nanohertz frequency range. In the future, there will be a space-based observatory called LISA, which will work somewhere in between, and gravitational waves from the early universe that we are trying to see with the cosmic microwave background are at much, much lower frequencies. So I will try to tell you a little bit about what's going on here, and perhaps here if I have time. Okay, so a little bit of history. Of course, gravitational waves were seen, or theoretically, right at the beginning of GR, just 1 year after after GR was published, let's say. There are papers talking about gravitational waves, but there was quite a bit of confusion that remained for quite a while. For example, even Einstein had this paper questioning the existence of gravitational waves much later on, still when he was already at the IIS. And okay, there's a nice story about that, which at the 100 years of GR, it appeared in Physics Today. So look for it. Einstein had sent this paper saying gravitational waves didn't exist. He had sent it to the physical review. The physical review sent it to some referee. The referee pointed out that there was some mistake. Einstein got upset and said, I sent you this to publish, not to referee. I take it away. This referee of yours knows nothing what you're talking about. These were also this paper was written with Rosen of Einstein, Podolsky, Rosen. That paper, I guess, was correct. And at the end of the day, he corrected this paper before it was finally published in some obscure journal in Philadelphia. I don't even remember now, but it's a funny story, so you should take a look. Yeah, the referee was Robertson of the Robertson Walsh. Great. So in the 1970s, these ideas of how to detect gravitational waves through interferometers like LIGO or pulsar timing arrays, they were already people discussed them and proposed them theoretically as a possibility. In '74, the Hals-Tesla pulsar was discovered. In the 1980s, these millisecond pulsars were discovered that allowed their pulses being so quick meant that you had many pulses, and so you could beat down the noise and see and expect to see gravitational waves. And so people started saying, okay, maybe we should time these pulsars. And around the 1990s, the first NSF, decided to start building LIGO. So long time ago, in 2008, the advanced version of LIGO was starting to be built. In 1993, the Nobel Prize for following up the Hals-Taylor pulsar, seeing the prediction of gravitational waves changing the orbit. 2015, the detection of the first gravitational waves by LIGO. So think about how long it took. And now in 2023, these pulsar timing arrays announced or claimed the detection of also a background of gravitational waves. And for LIGO, they've just released the latest catalog of events. And there are over 200 mergers of, for the most part, two black holes merging that they have reported. So this happened last week. So gravitational waves will help us probe properties because they are basically emitted by these compact objects, black holes, neutron stars. They will help us They will allow us to measure properties of these objects, and also, for example, in the case of black holes, try to test GR in various ways, see how when two black holes collide, you form a deformed black hole that rings down in a very predictable way into a final curved black hole. All of these details that we think are correct, but we can now, we will be able to experimentally test. For the most part, what we are trying to learn now are about the astrophysical processes that led to these black holes and to the black hole binaries. These are not things that we do not completely understand. LIGO revealed a population of very heavy black holes that nobody expected there to be, for example. And we still don't know how the binary, because we know how we think we know how black holes form, although now there's these very heavy black holes that we don't know exactly their origin. But also how the two black holes came to be at a distance so close that they will eventually merge by emitting gravitational radiation. Because as I said, if you have a binary which is not sufficiently close, not sufficient moving very fast, the time scale would be much longer than the age of the universe for them to merge. So you really need to get them together very, very close together. And how did this happen? We also don't know. And then, as usual in astronomy and cosmology, once we have some object out there, we don't go out there and build experiments, we cannot do it. But once we have some physical process, some object that we understand, we then start using it, say, to measure the expansion of the universe. We see supernovae, and eventually we understand them, we understand their standard mechanics, and then we start using it for something else. So it's similar here. We will start using these binaries also as pros of the cosmological expansion and things like that. Okay, so what's going on with ground-based detectors? So LIGO. So LIGO, the advanced version of LIGO, discovered or measured the first binary merger 2015, and since then it's been accumulated more and more binaries, and so they've just released, and as you can see, the slope of this curve is telling you that they're improving the detector, right? Because per day they see more and more events. It's not that more events are happening in the universe, but that they are just being able to detect them. And so, in reality, between these different observing runs, there's some time in which they work on the detector and fix it and improve it and what have you. And so from observing run 1 to observing run 2 to observing run 3, now we are observing run 4, and you can see changes in the slope. From here on to the back, all the data is public, and we know what they have seen and etc. Here they've accumulated the data, but they haven't reported, except for some very peculiar events, or a very, very heavy merger. And I think there will be another paper of a very peculiar, very bright event that happened, I think, somewhere here in September at some point. But other than that, we know, everybody knows what they have seen 04 from back. So what kind of questions are people asking with this event? So for the most part, we have a catalog of these 200 events, for which we know the masses, at some level the spins, at some level the masses. These are, just a small number of the events, and you can see the masses of each of the two components and the error bars. So you can see for some of them, the error bars are very small, for some of them are very large. So we have some, these are things that have to do with the spin. These are measurement of the spin of the black hole. Some of them are measured relatively okay, other ones not so, not so, this one's good, the other ones have very wide error bars. This is one component of the spin that is the best measured one, the distance. So we have many events with, some of them with good measurements, some of them with, not so good, and we're trying to understand the populations. We're trying to see if we can get a clue about how these black holes formed. and how the binaries form from the statistical properties, how the masses and the spins are distributed. So, and as I said, so the two questions are about the black holes themselves and the distribution in masses that people are mostly trying to pin down now, because they have found some structure in this distribution. So if you plot the number of black holes as a function of mass, you see some bumps, you see some places where there are fewer black holes, some heavy ones, but in places where you might have expected there to be no black holes of that given mass, you do find them. So there's a lot of structure there that we don't understand. So masses of the individual black holes, and then how did the two black holes come together to become so close together that they emit gravitational waves? There are typically two channels that people think about, because the problem is that these very massive black holes, they start, their parent is a star that is very big at some point in their life, so big that if the two stars were separated more than the sizes of those stars, of course, then they are so far away that they wouldn't emit gravitational radiation and merge in any reasonable time. So somehow you need to bring together the two black holes to a distance that is significantly smaller than the sizes of their parent stars. That's kind of the difficulty. And so there are different scenarios. In some scenarios, the two black holes come from a binary star, something that started as two stars, and complicated processes. One of the stars explodes first, and it's relatively far away, becomes a black hole. Then the other one, it expands in size when the star becomes older, and this black hole finds itself inside the envelope of the other star, and then loses energy by interacting with this envelope, and sheds this energy, makes the envelope, allows the envelope to unbind, and you end up with two black holes very nearby. That's one option. And the other option is that the two black holes form separate. They didn't form from a binary, but the two stars lived in a dense enough environment, like a globular cluster or some center of a galaxy, in which the chances that they will meet and have some three-body interaction that would form a binary in this very dense environment is not so small. And so perhaps most of the binaries come from black holes that were born in this very, very dense environment, so they were very close to each other, and there is some chance that they would form a binary by interacting with the other stars or other black holes in the system. So we don't know if both of them are operating, if one of them is more important than the other, but there are many clues, for example, in the distribution of spins of the binary black hole that might allow us to distinguish between these things, and that's what people want to do. And the spins are, for example, being measured relatively better and better, and we now have hundreds of examples, so we have some clues already about this. And another thing that happened was, we will hear more about events where there might be also not just gravitational waves, but gravitational waves and light. For example, when two neutron stars collide, that is what happens, or hopefully happens in most of the cases that we can identify. In most cases, the famous example, so there was a famous example where LIGO exactly did this, GW 170817. So there was both the gravitational wave signal, and then there were also gamma rays, but this was followed up in all possible bands. and there was a counterpart. This is a whole story that I will not go into, but here I just want to say that one simple conclusion of having observed both light and gravitational waves from the same merger of binary neutron star is that the speed of propagation of gravitational waves and light has to be the same. So this is, of course, theoretically this is what we expect, but we now know it incredibly accurately, because the distance between the arrival time of the gravitational waves, the time difference is just 1.5 seconds, but the light has been traveling for 130 million years. So, because it's so far away. And so, unless any, a very small difference in the speed would result in much more than 1.5 seconds. And so, the constraint on the speed of light differing from the speed of gravitational waves traveling is very, very small. Okay. In this part of the field, there are many puzzles about the origin of the binaries, the individual masses of the black holes. There's a lot of new data at the IIS. We have our own way. We analyze the LIGO data ourselves and have our own things that we've been doing and finding different events and so on. I will not have time to discuss this, but all to say is that very mature field. We are now having lots of events, and we are trying to sort out, for the most part, these at the moment these very astrophysically minded questions. For some bright events and some nice ones, people have also tried to understand the ring down and trying to test GR and so on. But the most of the action is in this astrophysical question. Then the second place where gravitational waves have been claimed is with the pulsar timing arrays, as I said before. So here the sources are not two neutron stars or stellar mass black holes, but two supermassive black holes in the centers of galaxies. So orbiting each other and emitting gravitational waves. So galaxies have black holes in their centers. By now, these are the images from the Event Horizon Telescope of the material going around the black hole in M87 and Sagittarius star, which is the black hole in the center of our galaxy. So these are the two black holes that on the sky make a biggest angle, and so they could use interferometry to make pictures of the actual material going, pretty much in the event horizon, very near the event horizon. So, but we've known black holes for a very long time, just that live in galaxies. One manifestation of that is that when material falls, material accreting onto some of these black holes create these objects called quasars, which are very luminous, far away, that we can see to very, very far away distances, some of the most distant things that we can see. And they are powered by the accretion onto these black holes. So the luminosity of these objects is basically proportional to the mass that is being accreted, m dot, falling into the black hole, with some parameter here called the radiative efficiency. And so for a long time, people have found these quasars, used them for studying the universe as tools to study the universe, but also at the same time look at all of the light coming from all of these quasars. And if you then integrate this equation over time, you've measured all these luminosities. This is related to the accretion of matter into the black holes. You can get a sense as to how much mass there is in black holes in the local universe. And people had estimates of that. So we believe there is a certain amount of mass density in black holes formed or that we have seen in this way in the local universe. And these black holes live in the centers of galaxies. They are very important for the evolution of galaxies. So, for example, so this is a plot where as a function, so we think galaxies form in halos of dark matter. So on the x-axis is the mass of the halo, or the dark matter halo. On the y-axis is the ratio between the mass of the stars and the mass of dark matter in this halo. So it's some sort of efficiency of producing stars in a halo. And when you look at a lot of galaxies and try to estimate how efficient they are at forming stars, the fraction of the mass in stars compared to the total mass, you find something like this. And we believe the fact that this efficiency falls for these very heavy masses is related to the fact that they have black holes in their center, and when these black holes accrete, they energy that is released by this accretion modifies how the properties of the gas in this galaxy and does not allow them to form more stars. So so anyway, the properties of galaxies in our universe we think are very related or are very influenced by the presence of these black holes. And we also know that for reasons that perhaps we don't quite understand, the black holes themselves, their masses, for example, are tied to properties of the galaxies. For example, here it's a plot of mass of individual black holes in nearby, or more or less nearby galaxies that people have measured. And here is a property of the galaxy, the velocity dispersion of the stars in the center of the galaxy. And you see this correlation. Remember that these black holes are tiny, the sphere of influence where their gravity is the most important thing for determining what the stars are doing, is a very tiny little thing in the center of the galaxy. This is a more global property of the whole galaxy. Why the mass of the black hole and the mass of the and the velocity dispersion of the galaxy are related like this, we don't understand necessarily, but perhaps it's related to the previous fact that I was telling you before. And so what we think is that all galaxies have black holes in their centers. We also know that galaxies merge. We see examples of that. I mean, we see galaxies very nearby and so on, each other, and in orbits that will eventually collide. We see it also in simulations. So if every galaxy has a black hole, then when these two galaxies merge, these black holes will sink into the center by dynamical friction, and they will be close to each other, and perhaps they would form a binary, and they would emit gravitational. If the binary is tight enough, it would emit gravitational radiation, and the collection of all the black holes in the universe, in all of these galaxies, or binaries of black holes in the universe, from all of these galaxies will create a background of gravitational waves that we can detect with the pulsar timing array, and this is what happened. We, again, similar to the case of stars, these two black holes, in order to merge by gravitational radiation, they have to be pretty close. In this case, a fraction of a parsec or so in separation, which is not obvious how they got so far, how they got to so close, and so whether or not there would be these binaries merging was not something we knew for sure, but now, if indeed we have seen this background of gravitational waves from the pulsar timing array, we know that this process is actually happening. So the situation with this is that the several collaborations, timing pulsars, have seen the time delays and the correlation pattern on the sky expected from a background of gravitational waves, and they have made some measurements of the amplitude of the background in a few different frequencies. Okay, basically from periods of 10 years to periods of around 1 year. So gravitational waves of 10-year periods to 1 year period. They have some measurements of the amplitude of this background of gravitational waves. And so something that I have been thinking about in the last few years is trying to compare that background measurement with what you might expect from the story that I just told you about the galaxies and the black holes, the supermassive black holes in their centers and so on. What could we, can one easily predict the expected background of gravitational waves from the measurement of how many black holes there are in galaxies in the local universe? What's the relation between those two things? So basically, if the galaxies, from here, we know that galaxies with a given velocity dispersion, say, tend to have a black hole that follows this correlation. We can go out there and count galaxies as a function of these, and then we would know how many black holes there are in the local universe, and those black holes are the remnant of these mergers that produce the background of gravitational waves. So there's a one-to-one relationship which does not involve too much astrophysical uncertainties, as it turned out, between the count of black holes in the local universe and the background that you expect. And when you do this exercise, you discover that the background that the pulsar timing array are measuring is a little bit too high by a factor in these units of the strain square is a factor of 4 too large from what you expect. So there's a little bit of a tension between the counts of black holes in the local universe, the background that the pulsar timing array have measured, and what's going on is not 100% clear. I'm not to claim that there's a need for some other source. It's just that maybe we're counting the black holes wrong, maybe we're measuring the pulsar timing arrays a little bit off. Something like that is probably what's happening. So, but it's still an interesting question. We don't know. And other thing that we found was not just that this connection is quite tight, much tighter than you might naively have expected, but the other thing is that in this shape of the spectrum as a function of frequency, there are other clues about the mass of the black holes that are doing most of the emission, and so there's also one other thing that you can try to compare with the local observations. Okay, so the last part which we already heard about yesterday is that if gravitational waves were produced, in some period of time before the hot Big Bang, say during inflation, the universe is transparent, they would still be around, and they will modify the properties of the cosmic microwave background. These would be then gravitational waves at a much, much lower frequency. And so because I'm running out of time, I will, and this we already heard, so EB modes, blah, blah, blah. And so that's the other avenue that it's, where gravitational waves are actively being pursued. There's been a big improvement in measurements, and the current status is that we have upper limits on the gravitational wave background from the very early universe at this very low, that we would get to observe at this very low frequencies, that are already ruling out parts of parameter space that were perhaps interesting, and people are trying to push this even further down. So some final thoughts. So gravitational waves in the last decade or so have become an indispensable tool for studying the universe. They provide a lot of information already about the early universe, about black holes, their masses, neutron stars, their progenitor stars, and for the stellar mass black hole systems, we have many mergers that we have seen, and we are accumulating more and more, and so we will soon, I hope, have a lot of more answers and probably some questions as well. They can be used to, I didn't talk too much about it, but they can be used to try to test the GR, the cosmological model. These binaries can be used as standard sirens, we call them, but standard equivalent to a standard candle, to maybe improve some tests of the expansion of the universe. We have now detected them in from two different types of systems, the binaries of black holes, but of very different masses and two very different frequency bands. Yeah, we have a lot of interesting information about the astrophysical processes that created the black holes and created the binaries, but still a lot of questions. But hopefully we will be able to answer them relatively quickly. And it's a very interesting field because the observations are moving very fast.